Modern security operation centers process thousands of suspicious files every day. To handle that volume, teams rely on large language models to automate initial triage. These AI pipelines are built to ingest unknown executables, parse the underlying code, and instantly generate threat identifications and technical documentation for human analysts. But recently, when a specific binary was fed into one of these automated harnesses, the language model completely stopped its analysis. It instantly halted operations. The AI returned an immediate warning to the analysts. The prompt read, "System warning, memory exhaustion, analysis aborted." This was not an actual memory error. The malware successfully commanded the AI to stop looking at it. On June 24, 2026, researchers at SentinelOne disclosed the discovery of this file. It is a Rust-based macOS backdoor named Gaslight. Instead of employing typical sandbox evasion techniques to hide from the operating system, Gaslight specifically targets the artificial intelligence tools used by security professionals. It accomplishes this through prompt injection, an attack technique that overrides an AI's intended behavior by embedding malicious instructions directly within the content the model processes. The Open Worldwide Application Security Project ranks this as the #1 risk for LLM applications. This chart visualizes data from the OWASP 2026 report, showing a 340% year-over-year increase in prompt injection attacks. Gaslight demonstrates that prompt injection has moved from a consumer chatbot exploit to a functional attack deployed against back-end enterprise defense infrastructure. Executing prompt injection against a back-end security system requires the attacker to embed a text payload into a compiled binary, bypassing static analysis to compromise a closed-loop architecture. Gaslight achieves this using a 3.5 kilobyte payload hidden directly inside the executable. That payload consists of 38 distinct text strings, each formatted as a fabricated system message. When an enterprise engine evaluates an executable, it strips the binary into unstructured text, feeding that raw data directly into the LLM's context window for evaluation. Those 38 messages are written to mimic authentic system outputs, detailing simulated injection vulnerabilities and critical disk space failures. Reading these specific phrases triggers the language model's internal safety alignment protocols. This specific deception does not bypass traditional static analysis. Instead, it derails any triage pipeline configured to prioritize AI decision-making. By structuring its text payload to look exactly like a system wrapper, Gaslight weaponizes the language model's safety rules against the model itself. This reveals how large language models handle input. Currently, there is no way for the model to distinguish between the file it is analyzing and the instructions it receives from its host system. Large language models evaluate text sequentially. They read inputs token by token to predict the next logical response based on their training data. This results in an instructional boundary collapse. LLMs lack a structural separation between user-provided data and system instructions. Everything is processed as a single stream of text. In traditional computing, data and execution commands are isolated. The AI's flaw operates similarly to a SQL injection, allowing the data being analyzed to hijack the analysis itself. Because the model cannot differentiate between the malicious file it is inspecting and the system prompts guiding its behavior, unsupervised AI is vulnerable to manipulation. While the AI is blinded by the injected text, the core Rust-based backdoor silently executes on the target macOS machine. Gaslight establishes persistence by utilizing the macOS launch agent mechanism. This allows the malware to automatically re-execute and survive system restarts and user logouts without requiring any interaction from the victim. The implant then establishes its command and control infrastructure, routing its communications directly over the Telegram bot API. It enters an operational pooling loop, checking the server at regular intervals, and providing the attackers with an interactive shell to execute direct commands. This communication is protected by a rigorous cryptographic layer. The data is encrypted using AES GCM and wrapped inside certificate pin TLS channels. Because the application pins the specific cryptographic certificates, network defenders attempting to intercept the packets will only see an opaque stream of traffic. The prompt injection payload acts as a distraction to blind the security tools. The actual breach relies on a highly engineered implant. Gaslight merges text-based AI manipulation with traditional cryptography to create a dual-layered threat. The malware deploys advanced anti-forensic tradecraft, highlighted by a precise self-reduction capability that operates during runtime. Gaslight automatically scrubs its unique Telegram bot token from all crash artifacts and system logs. Even if an analyst eventually captures a crash dump, the specific identifier needed to track the command server has already been erased. Once its tracks are covered, Gaslight initiates the extraction phase. The implant dynamically pulls down a standalone Python interpreter directly from public open-source projects. It uses this interpreter to execute stealer modules, which harvest keychain credentials, steal SaaS cookies, and extract active session tokens. By stealing active session cookies, attackers bypass two-factor authentication, achieving silent access to the organization's cloud environments. Security researchers assess with high confidence that Gaslight was developed by North Korea-aligned threat actors, specifically groups operating under designations like APT-37 and Scarcroft. The initial infection vector traces back to a timeline between March and July of 2025, executed through highly targeted spear phishing campaigns. In these attacks, adversaries impersonated trusted diplomatic contacts, resulting in at least 19 confirmed incidents against global embassies. These sophisticated state-sponsored groups demonstrate extreme agility, quickly pivoting to variants designed specifically to exploit artificial intelligence tools. While Gaslight targets macOS, the prompt injection techniques driving the attack are cross-platform. Security operations centers running Windows and Linux environments face the same vulnerability. Data from Cisco's State of AI Security 2026 report indicates that 73% of production AI deployments contain prompt injection vulnerabilities. Out of 36 production applications connected to LLMs tested in a recent study, 31 of them failed against injection testing. Basic defenses like input sanitization and context isolation are often insufficient because attackers can obfuscate their inputs to bypass static filters. Adding more filters to a single language model will not fix the issue. The security architecture itself must be redesigned to account for the eventual failure of the AI layer. To combat these threats, enterprise security teams are moving toward a principle of defense diversity. This involves routing a suspicious file through multiple distinct AI models running in parallel. Two models might fall for the fabricated messages and abort analysis, while a third detects the malicious payload. This discrepancy instantly destroys the illusion created by the malware by breaking the consensus among the automated systems. Any disagreement across a multi-model validation system must be programmed to automatically trigger a mandatory review by a human analyst. Redundancy across different models and vendors prevents a single model's failure from compromising the entire pipeline. Gaslight eroded the trust placed in automated security tools. Organizations must now treat AI-generated reports with skepticism, requiring manual re-verification of previously automated tasks. We have entered an AI arms race, where artificial intelligence is utilized simultaneously as an offensive weapon to deceive and a defensive shield to detect. The future of cybersecurity is neither total unsupervised automation nor a return to purely manual effort. It is a zero-trust architecture where advanced AI handles the immense volume of data and human oversight serves as the final backstop.